Work can either be positive or negative. Work is positive if the force makes an acute angle with the displacement, meaning the object gains energy. Work is negative if the force makes an obtuse angle with displacement, meaning the object loses energy. Work is zero if it makes a right angle with displacement, so no energy is gained or lost by the object. Cosine in the work equation will take care of the sign. For acute angles, cosine outputs a positive number. For obtuse, it outputs a negative number. And for right angles, cosine is 0. If the angle between the force and displacement is 0 or 180 degrees, we don't even need to use cosine. But if you're just in the habit, then that's fine too. Cosine of 0 degrees is 1, so if force and displacement are in the same direction, you could just use FD. If the force is exactly opposite displacement, 180 degrees, you could just use work equals negative FD. For that one, I don't know if you need to trust yourself. You could just FD cosine theta, and then when you take cosine of 180 degrees, then you'll get the negative 1 there. So let's look at it in action. We've got a new situation where a horizontal force, it pushes a cart up the incline, a distance d. The force does work on the cart, giving the cart energy. The angle between F and D is the same as the incline angle theta. So to calculate work, we can just do FD cosine theta. Displacement, displacement, force, force. Just moved down here so you can see the angle is the same. Another way to calculate work is to change the force into components, parallel and perpendicular to displacement. If we do this, then work equals the parallel component of the force vector times displacement. Sometimes it's easier to use this method to calculate work. Third way to calculate work is to change the displacement into components, parallel and perpendicular to force. The component of displacement is parallel to force is d parallel, and the component perpendicular is d perpendicular. When we do this, we can find the work using work equals force times the parallel displacement. The big thing here is force and displacement have to be in the same plane. So they have to be parallel to each other. If they're not parallel, you can resolve it into components to get the parallel one. In summary, if force F is parallel to displacement D, work equals FD. If F is perpendicular to D, then work is 0. There's no need to use cosine in those two special cases. If the F vector makes an angle theta with the D vector, then we can calculate work by plugging into the equation work equals FD cosine theta. Finding F parallel, the component of the force parallel to the displacement, and plugging in work equals force parallel times displacement, or finding displacement parallel, the component of the displacement parallel to the force, plugging in work equals FD parallel. In all cases, if F makes an obtuse angle with D, work is negative, and if F makes an acute angle with D, work is positive. The AP Physics equation chart has work listed in the following way. Change in energy equals work, which equals F parallel times displacement, which equals FD cosine theta. Change in energy equals work reminds us that work is a change in energy. It's not a type of energy, it's the change in energy. Work equals force times displacement. Tells us that only the component of force parallel to displacement does work. It's up to us to remember we can do work equals FD displacement, if you like to. Pick one of those three ways to solve the problem and just stick with it. That's my advice. Where we make the displacement into a component parallel to the force. W equals FD cosine theta is just the basic equation for work. It's up to us to remember we can drop the cosine if needed. Just note that these equations for work only work if the force has constant strength. If the force has changing strength, there's our equation on the equation, then we need to represent the strength of the force on a force versus displacement graph. An example of force versus displacement graph is shown where the force becomes stronger during the first meter the object travels. Then the force becomes weaker as the object travels during the next 3 meters. Work is the area of a force versus displacement graph. We already know that because if we multiply the y-axis by the x-axis, F times x, or F times d, that would give us our area. If we divided F over x, that would be Newton per meter. Not anything useful, unless there's a spring involved. If there's a spring involved, then yeah. All right, so we have the green triangle's area is 225 joules. This means the object gains 225 joules of energy as it travels from position 0 to position 1 meter. Okay. The blue triangle's area is 675 joules. This means the object gains 675 joules of energy as it travels from 1 meter to 4 meters. So for the entire 4-meter trip, the object gains a total of 900 joules of energy. Note that this means the object sped up because it gained kinetic energy. So just because the force ended doesn't mean the motion ended. Because remember, that's the same thing as no longer accelerating an object. Force and acceleration are proportional. So if you're no longer accelerating an object, that doesn't mean the object is stopped. You can be moving with a constant speed, or you can be at rest. At rest would be actually stopped.